In this video I'm going to talk about polarization by reflection. So let's consider in a general case here I have unpolarized light, and I've kind of drawn that as as electric field of many different directions, essentially all equal magnitude. So this is kind of a circular pattern to show that it's totally unpolarized, and that could be coming directly from the sun, or it could be coming from incandescent light bulb or any other source of unpolarized light. And that incident light, I'm having it reflect off this boundary between different media. And for this examples, I'll be talking about air as the media that this incident light's coming through and reflecting back through, and then it's refracting off this media, for example, water, glass, asphalt, etc. And so this unpolarized light's coming, and in general, when it reflects up, I kind of have an eye kind of showing there to see what would see with this reflected light, which reflects off that boundary. I would see that it's partially plane polarized. So therefore, the electric field is not uniform strength at all angles, but what it does is it kind of has polarization which is greater, which is parallel to this boundary. So for example, if this is horizontal, it would have a greater horizontal component than vertical. So that's what happens to the reflected one in general. So now if I kind of look at an eye kind of here looking at the refracted one, we see the refracted one, the refracted signal that goes through into this new media is also plane polarized, but it's kind of plane polarized opposite, where this one contains more of the signal which is parallel to this boundary. This one contains more of the signal which is perpendicular to this boundary. And then, as always, Snell's law works, and I could calculate this angle of refraction. And also, we know angle of incident always equals angle of reflection. So as this angle changes, different polarization effects happen on the reflected and the refracted signal. One case would be if the incident light is coming straight into the boundary, and it's unpolarized. What happens is both the reflected signal that I would see here or the refracted signal I would see here would both still be totally unpolarized. And I kind of drew them as smaller circles because not all the energy was coming in incident, and then all parts of it get split between refracted and reflected. So, but there turns out to be one angle which is unique. And if you kind of look at this, so for non-metallic reflective surfaces such as water, glass, asphalt, diamond, there is a particular incident angle which is at the ratio of the index of refraction of what it reflects off of. So this is has to be the N2 over N1, the index refraction of what the digital signal comes in. If it solves this relation where that equals the tangent of the angle, or you can think of, if I wanted to find that angle would be the inverse tangent of the index of refraction of what it reflects off of over the index of refraction when it starts in. And it's important, if I switch those, invert those, I get the wrong answer. So it's always important to remember N2 over N1 is this Brewster angle. At that one particular angle, the reflected signal that I would see is 100% plane polarized. It contains no components of this electric field, which is going to be perpendicular to the boundary. So even though I had the unpolarized light coming in, I would reflect off, and I would be 100% plane polarized. And since we know that in any case that angle of incidence equaling angle of reflection, we also know that this angle here, angle of reflection, is also this value. And now we always know for every case, Snell laws always holds true, where N1 sine of theta 1 equals N2 sine of theta 2. So I can solve for theta 2. In this condition, just like every other condition, well, except when I come straight in, the refracted signal will be partially polarized. And since this one contains nothing which is vertical, nothing which is perpendicular to the boundary, everything parallel to the boundary, this one once again contains more of the signal which is perpendicular to the boundary. But kind of what's even more interesting in that, if you could, and I'm not going to do the trig right here, you certainly can do that yourself, that at this one unique angle of the incident angle, which also happens to be the same angle as reflection angle, if I solve for using Snell's law, I can solve for Brewster angle, and I could also solve for, which is that one unique case. I could also solve for theta 2. We're going to find for this one unique case that the reflected signal and the refracted signal are perpendicular to each other. Those are 90 degrees. That's the only case that happens. And obviously, I mean, both these angles change with the media on both sides, n1 over n2. So as a quick check on that, let's do a case, and let's assume that we have air, that the incident angle comes in, and it's going to the second media is water, then glass, and then asphalt. So water at 1.33, glass at 1.5, asphalt 1.635, and air is 1.003. So I want you to solve for the Brewster angle and then the angle of refraction. So why don't you pause the video, solve for those cases, and then we can start back up and we can check. Here are my solutions. You take the index of refraction of what it reflects off of over the index of refraction of what it starts in. So start from water 1.33 over 1.003, find that n, take the inverse tangent of it, and I get a Brewster angle. That would be my theta 1 now. And then using Snell's law, I can take the sine of that, multiply it by the index of refraction of what it starts in, divided by the index of refraction what it reflects off of, or refracts into, and then take the inverse sine of that, and I find my theta 2. So for water, turns out Brewster angle 53.05, refraction angle 36.95. For glass, Brewster angle 56.30, refraction angle 33.70. Asphalt has the greatest Brewster angle, and angle is always measured from the perpendicular, 58.54, 31 and the refraction angle is 31.46. And if you add this one up, that becomes 90 degrees. This is also 90 degrees and also 90 degrees. So you wouldn't even, for cases where you have the Brewster angle, if you get an answer here, you just take the fastest way to get refraction angle is take 90 minus that angle gives you the refraction angle, and that's a good check. In my everyday life, why would I even care about Brewster angle? I'll give you an example. Let's say it's 6 o'clock in the evening, and you're fishing, or you're a lifeguard and you're kind of looking into the west, and you have the incident lights now at 6 p.m. is coming in at this angle, and you're kind of looking westerly, and you have this reflected light going off the water, and what you're seeing is you see what's called glare. You see all this, you see electric field, everything horizontal, so there's all that it appears to be, it's hard to see. You see this reflection, and then let's say later that evening, maybe like 6:30, again let's say you're driving your car to the west, and so the sunlight, which is unpolarized, is coming, reflecting off the asphalt, and you're driving, and it's going right in your eyes, and again you see this fully plane polarized glare, electric field, which is horizontal when this angle is now such that it's 58.54 degrees. Now you see this glare coming off the asphalt, and it's hard to drive. I have a question kind of relating to that. So if I'm fishing or we're driving and the reflected light is causing glare, which affects your ability to see, which one of these two polarization transmission axis sunglasses should you use? Should you use the one that has where as shown right here, the horizontal polarization transmission axis is horizontal? Or would you want to have where the polarization transmission axis is vertical? So pause the video, think about it, and then we'll talk about it. Polarized transmission axis means that it transmits polarized light that's parallel to it, so it doesn't stop it. Well, if this reflected light's coming off is already horizontal, then having this, so this one will have this incoming horizontal polarized light coming to it. It'll transmit all of it through to you, so you would see all the glare. This one, since the polarized light is coming horizontal, and this only transmits, the only thing that makes it way out on the back side is one's at vertical, it would stop all this polarized plane reflected horizontal light. And so because they're at 90 degrees to each other, the transmission axis and the incoming polarized light, none of this reflected polarized light would get to the driver or the person fishing. So you would want to have this sunglasses, because this would do you no good at reducing this plane polarized reflected light that's causing your glare. Now I have two problems, and each problem has multiple parts. The first one, I'm going to have direct sunlight of an intensity of 1,000 watts per meter squared going directly to the polarized sunglasses, and I'm looking directly at the sun with the polarized sunglasses. And I have three different types of glasses I could have on, A, B, and C. The only difference is the polarization transmission axis. A is the axis is horizontal, B, the polarization transmission axis is vertical, and C is at 40 degrees from horizontal. And so the question is, what's the intensity of the light which passes through the sunglasses? So give me an answer for 1A, for 1B, and 1C as far as intensity. And now another question is, if the light passes through, is the light that passes through each one of these sunglasses polarized? So you can answer that question as well. And now the other part is, if so, what's its direction? What's the direction of A, what's the direction of B, and direction of C of this potentially polarized light which passes through it? Now 2 is very similar. So we have the same three sunglasses, and basically the same questions, but this time, instead of having the sunglasses looking directly at the light, I have the sunglasses looking directly at reflected light, and the reflected light, so I have water, air, and then reflecting off water, and we're going to have the case where the incident light is the Brewster's angle. So I'm going to light from the sun at the Brewster's angle, so sunlight at the Brewster's angle relative to the perpendicular between this air and water interface. It reflects off, and now this light, reflected light, which originally started from the sun, has an intensity of 300 watts per meter squared directly toward these polarized sunglasses. Again, the same three sunglasses. The same first question is, what's the intensity of the light which passes through the sunglasses? So what's the intensity of light which passes, in this case, for each one of these? And for this part 2, let's assume that we're just talking what's the intensity of the reflected light. So what's the intensity of the reflected light? So let's not consider any direct light which may go through those sunglasses. So what's the intensity of this reflected light only, which passes through sunglasses A, B, or C? A, B, and C, so 3 different answers for 3 different intensities. Is the light polarized for each one of these cases? So 3 different answers there, and then also 3 different answers. So if so, what is the polarization direction for glasses A, B, or C? So pause the video, solve, and then we'll have the solution. Here's the answers I got for number 1. The intensity for all 3 glasses which exits the Polaroid sunglasses is 500 watts per meter squared, and the directionality of the polarized light which exits the sunglasses is the same direction as the transmission axis. So in the first one is horizontal, then second B is vertical, and C is at 40 degrees from horizontal. Number 2, 2A, it's 300 watts per meter squared, and it's the polarized light which goes through the glasses A is horizontal. For 2B, it's 0 watts per meter squared, and for 2C, it's 176 watts per meter squared, and the polarized light which goes through the sunglasses is at 40 degrees to horizontal. If you didn't get those answers, we'll talk about it. Number 1, direct sunlight is unpolarized, which means it has electric field in all directions, and for that case, when I have unpolarized light coming to a first polarizer, the intensity of light that passes through the polarizer is 1/2 the intensity of the unpolarized light, which is coming towards it. And since the intensity coming towards is 1,000 watts per meter squared, half of 1,000 is 500, and that's why it's 500. And in all cases, once I have a polarized sheet, it exits and it's plane polarized, and it's plane polarized in the direction of the polarization transmission axis, which accounts for these angles. For 2, only because I have the incident light coming at the Brewster's angle, the reflected light will be 100% plane polarized. So therefore it's already horizontal. So this reflected light is plane polarized horizontal. And so therefore the equation I'm going to use is, if I have plane polarized light it's already plane polarized and it's coming to the polaroid, the intensity of this plane polaroid light entering coming towards that polaroid times the cosine squared, the cosine of theta squared, where theta is the angle between the polarization transmission axis and the plane of polarization of the incoming light. Find that theta, take the cosine of it and square it, multiply it by this intensity, and that gives me the intensity of the polarized light which passes through the polaroid or exits the polaroid. So we need to find this, since in all these cases I already have plane polarized light coming toward it. So I'm going to use this equation. And in every case, the intensity of this plane polarized light is 300. It's 300 watts per meter squared. Okay, so what I need to find is the angle between what this incoming light polarization angle is and what the glass's transmission angle is. Well, so it's horizontal here coming in. The glass's transmission angle is also horizontal, so theta is 0. Cosine of 0 is 1, squared is 1, therefore I get 300, and what exits is also plane polarized, still in this horizontal plane. For number 2, the polarized light which is coming to these glasses is horizontal, the transmission axis is vertical, therefore theta is 90 degrees, cosine of 90 degrees is 1, cosine of 90 degrees, is 0, square 0 is still 0, so I get the answer of 0. For C, the incoming light is horizontally polarized. That's 40 degrees difference between the transmission axis and the incoming light. So cosine of 40, square it, times 300 gives you approximately 176 watts per meter squared. So those are the answers.